Okay, welcome back. We are going to continue with our example 11.11. And again, this is asking to calculate the gauge pressure inside a soap bubble with a radius of 2.0 times 10 to the negative 4th meters, using the surface tension for soapy water in this table and convert that pressure to millimeter mercury. Okay, so the first thing is we want to note how to calculate that gauge pressure, and that is what I briefly mentioned in the last video. Okay, so gauge pressure, P, you can say gauge right here, is equal to 4 times the surface tension, gamma, divided by our radius. Okay, so we need to figure out what our surface tension is. And again, that is for a soapy bubble, and it should be in this table 11.3, which is here. Yes, okay. So we have our liquids and then our surface tension on the right-hand side. So we just go down to find what we're looking for, which is soapy water. Okay. So our surface tension is going to be 0.037. Okay, so 0.037. And it tells us the units as well, because I did not mention that last time. Our units are going to be in newtons per meter. Newtons per meter. So I guess I should add that. Our surface tension is in newtons per meter, which makes sense because we have a force divided by a length. Okay? All right, so now in this equation, we can go ahead and plug these values in. We have our surface tension, 0.037 Newton per meter. Divide that by our radius, which is 2.0 times 10 to the negative 4th meter. Okay. And so if we plug that into our calculator, 0.037 divided by 2 times 10 to the negative 4th, we get 7.40 times 10 to the 2. Okay, and this is going to be in pascals or Newton per meter squared. Okay, we can also say it's 740 pascals. Okay, so this is our gauge pressure. Okay, now if we want to convert this to our millimeters of mercury, we'll take this value, 740, and use this unit conversion here that I wrote down earlier. And so 1 millimeter of mercury is going to be equal to 133 pascals. So we take the value that we just found, 740, and divide it by 133, and we get 5.56 millimeters of mercury. Okay? Alright, so that one wasn't too difficult. We just need to understand how to use that table. Okay? Alright, so now that we talked about cohesion, let's go ahead and talk about adhesion in liquids. Okay, so adhesive forces are going to also be attractive forces between molecules, but now of different types. Okay, so maybe a water molecule and an air molecule. Okay, and there's a couple of ideas that we need to understand, and that is contact angle and capillary action. So the contact angle is going to be the angle tangent to the liquid surface and the surface that it is on, okay, or touching, in contact with, and that's directly related to the relative strength of the cohesive and adhesive forces. Okay, so that contact angle, let's look at this example here. Let's say between wax and water, the contact angle will be between the water, okay, the surface of the water and the surface of the wax, okay, and this is going to be a larger angle because if you think about water and wax, it kind of like beads up on wax. And then the other example is going to be paint and water, and that angle is going to be much lower, okay, because the water tends to kind of spread out on paint, right? Okay, so what about capillary action? That is the tendency of a fluid to be raised or suppressed in a narrow tube or a capillary tube. Okay, so believe that is in this figure here. It kind of shows the that tendency, and that's based on the density, okay, of that substance. Okay, so here's a better image. If we take two different substances, one that's more dense and one that's less dense, the one that's less dense is going to have a higher height here, excuse me, versus the one that's more dense. Okay. All right, and it does change with the size of this tubing as well, and that's going to be that radius here, I believe. Okay. All right, so that's the basic idea of the adhesion that we wanted to talk about, and let's go ahead and look at an example. Okay, I believe examples really help you learn rather than me just talking about things. Okay, so example 11.12, can capillary action be solely responsible for sap rising in trees? Okay, to answer this question, we need to calculate the radius of a capillary tube that would rise sap 100 meters to the top of a giant redwood, assuming that the sap's density is 1,050 kilogram per meters cubed. Its contact angle is 0, and its surface tension is the same as that at water at 20 degrees Celsius. Okay, so we need to first look up this surface tension. Okay, our surface tension is going to be based on that table here, and it said at 20 degrees Celsius. So here's water at 20 degrees Celsius. So here is our surface tension. Okay, 0.0728. 0.0728. That's in Newton per meter. Okay, let me just double check that. Okay, we're good. Okay, so we want to calculate the radius of the capillary tube. Okay, so let's go back. This is the equation that they're referring to. Okay, so let me copy that down. H equals 2 gamma cosine theta over rho times g times r. Okay, so we want to know the radius of the capillary tube. So let's go ahead and solve for our radius. R is going to equal what? Really just switching these two, right? So we have 2 times gamma cosine theta over rho times g times h. Okay, so all we have to do is plug in all of our values. Okay, so we have 2 times 0.0728 Newton per meter times cosine of 0 degrees, okay, divided by, our density, which is the sap's density, 1,050 kilogram per meters cubed. Our acceleration due to gravity is 9.8 meters per second squared. And the height that we're trying to raise, the sap is 100 meters. Okay, so we can plug this into our calculator. We have 2 times 0.0728 times cosine of 0 divided by 1050 times 9.8 times 100, and we get, let's see, hopefully I didn't make any errors. Okay, I get 1.41 times 10 to the negative 7th meters. Okay, so as you can see, our capillary tube would have to have a very small radius. Okay. All right. So moving on to other types of pressures, and that is pressures in the body. So we have a few different main ones I want to talk about is blood pressure and pressure in the eye. So with blood pressure, there is a maximum and minimum blood pressure that we'll have, and that's as we breathe, I believe. Okay, don't quote me. But we have two different blood pressures, the systolic and diastolic pressures, or the maximum and minimum blood pressures. One idea here is that, or one thing that we want to note is the pressure in the feet will be larger than that at the heart due to the weight of the blood, okay, which makes sense. We've been talking about this, the pressure and force, okay, pressure and forces, how they're related. Then we have the pressure in the eye. We have fluid pressure or intraocular pressure that maintains the shape of the eye. And when there is circulation of fluid in the eye is blocked, so when that circulation is blocked, it can lead to a buildup in pressure, and that is a condition called glaucoma. Okay, so this is just some interesting things that I found, and there are some other ones in the textbook if you are interested. Okay, let's look at an example talking about pressures in the body. Okay, we suppose that there is a 3 Newton force. We suppose that a 3 Newton force can rupture an eardrum. Sorry about that. Okay, if the eardrum has an area of 1 centimeter squared, we want to calculate the maximum tolerable gauge pressure on the eardrums in newtons per meter squared, and convert it to millimeters of mercury. So what we're going to do is find, for part A, find the gauge pressure, so P, and pressure, remember, is force over area. Okay, we know that there is some force, 3 newtons, okay, over our area, which is in 1 centimeter squared. Okay, we need to convert that, so that's going to be 1 meter per 100 centimeters. Square that and get 3.0 times 10 to the 4th, and this is in Newton per meter squared. I'm not going to convert it to millimeters of mercury just because we have done that a few times in the past, and I think we got it down. Now, what depth in fresh water would this person's eardrum rupture, assuming the gauge pressure in the middle of his ear is 0? We'll say that pressure equals H rho G, as we have in the past. Solve for H. We solve for H here, and then we plug our values in. We have our P from above, we have our rho from water, and G, and we get 3.06 meters. So that's the depth in fresh water.